I will now present a method from homological algebra that allows you to prove the Eilberg-Silber theorem by very abstract argument. And that method, called the method of acyclic models, is also useful in other parts of algebraic topology. For example, when you introduce the cup product and its various properties. So we have to start with some abstract notation here, which I introduce in a slightly more general fashion than needed later. So let C be a category, and for connoisseurs, a small category. And R will denote a ring and commutative ring. And then I will introduce concept of a module over a category. So an RC module is just by definition a functor from the category C to R modules. And the motivating example for that notion is when the category is a group. So remember that we can view any group as a category with just one object and the group elements as morphisms. And then such a module, if C is the category of a group, is just the group ring of the group. That's a ring that you associate with a group. I don't think it has appeared yet in the lecture.
No, I don't think so.
At least not at a prominent place. But if you want to look this up, this was the motivating example for this notion. Now, RC modules are very close. When we argue with RC modules, we will see that we can argue very close to what we're used to in the case of R modules. So first of all, we should say what is a homomorphism of RC modules. There's only one choice you could make. It's a natural transformation.
Mm-hmm. And maybe even easier, I mean, if the category has one object and the identity morphism, then an RC module is just an R module.
Yeah, exactly. So let's make this green. Homomorphism of RC modules is just a natural transformation. And let me put down this example that I mentioned. If C is a group, what is an RC or RG module in that situation? Well, there's only one object in this category. So a functor associates to each object in R module, so there's only one R module around. Therefore, it's an R module M. But together with a homomorphism from the group to the automorphism of M. Because a functor also maps arrows, so the morphisms, to morphisms of R modules. Since there's only one, all the morphisms are endomorphisms. What you really get is a map from G to the endomorphism of M. But since G is a group, so every element G has an inverse, so it's actually going to be automorphism of this module M. And this is the same structure as a module over the group ring, which is something that I don't want to spend a lot of time now. Just want to mention this. This is the same as an RG module structure on M. This is the same as the structure of an RG module structure on M. I'm not sure how to finish this sentence. And this guy here is the group ring. With RC modules, we can do homological algebra in a very similar fashion as with R modules. So the category, it turns out that the category of RC modules is an abelian category. So that's a notion that we mentioned several times. We never formally introduced what an abelian category is, and I won't do now. But I want to mention it and then say hands-on why we can argue very similar to the category of R modules. So for example, having a short exact sequence of RC modules. What do we mean by that? Well, a sequence of RC modules so we have maps from M1 to M2 to M3, and we write this as we do for R modules and call such a sequence exact if it is pointwise exact. Remember, these are functors, so if for any object in my category, if I plug it in, I get an R module, and if all these sequences I get then are exact. This is the notion of exactness. We also have a notion of projective module. This is easy because projectivity was defined by a diagram, and diagrams we can also draw in the category of RC modules. So, remind you of that. One defines projectivity of RC modules by the defining or characteristic diagram. So if you have something like that, you have a diagram of RC modules. So remember, these are natural transformation. The map from M to N is an epimorphism. So that is exact, just meaning that if I plug in any object in my category, then the map MC to NC is an epimorphism. So whenever I have this situation, I can lift the map from P, and I can lift the map from P to N to a map from P to M, then P is projective. So P is projective if for any situation like that, M and N, I can lift the map to a homomorphism of RC modules. Let me make the following remark, that being projective for any object So projective as an R module does not imply, in general, that M itself is projective as an RC module.
But the other way around it works?
Yes.
Okay.
Yes, the other way around works. So let me give you one example of a module that's projective, a module that's even what we would call free. So we define this module, definition. Let Ci be a collection of objects in C and then I can form a module as a direct sum. Again, direct sums of RC modules is also defined pointwise. And I form the following direct sum. What does that even mean? So what do we have here? Well, we have for each object C in capital C, I need to define an R module. Okay, so I have to be able to plug in an object C into this F. Well, I do this by plugging it in here, and then what I have is a direct sum of three R modules over certain sets, and the sets are the morphisms from this fixed object Ci to C. Okay? If you want this thing here, you can view as a covariant functor from C to the category of sets. And then I compose this functor with the free abelian, with the free R module, which is a functor from set to R modules, and then this is what you get. Right? So for each C, I can plug it in here, and I just have a bunch of free R modules. But I want to claim that this module it's certainly projective pointwise, even free pointwise, but I claim it's even a projective module as an RC module.
It's clear how it is a functor, right?
Say again?
It's clear how it is a functor, yeah? I mean, right now you declared it on an object.
Right, because, okay, maybe I can make this more explicit, but this is due to the fact that this is a functor. So maybe it's good to be more explicit on that. So if you have a morphism from C to C prime in C, then this implies or induces a map from Ci C to the morphisms from Ci to C prime just by composition. So you take such a morphism, you compose. So you have a map of sets, and the map of sets also induces a map of R modules on the free R modules over these sets. And this is how you get the structure of a functor. So it's actually not hard, it's just very abstract to think about these objects.
And you still take the direct sum of these.
And I take a direct sum of these, yeah. So I want to finish that definition. The definition is then this F is called free. And these objects Ci are called the models of F. It's just terminology. So usually we don't use free freely. If we say something is free, it's a left adjoint of a forgetful functor in some sense. You can indeed view this construction as a left adjoint of something, of a kind of forgetful functor, but I don't want to go into that. I want to rather take this just as a name and show that this module F has the property of a projective module. It is a projective module. So I want to prove the proposition that free RC modules in that sense are projective. And it is enough to consider not a direct sum, but just one of those. So it's enough to prove that for F being R morphisms from a fixed C, like that. Okay, so let's consider a lifting problem. Let's call that Q. Let's call that F. Remember, these are natural transformations. And what we need to construct is a lift F bar. That's our task. We need to look at what we have to do here pointwise. And first, that's the natural choice. We focus on the object C. That is somehow the defining. The model of F is this little c. So let's look at this lifting problem at little c. So first consider this situation. Okay, let's draw it exactly in the same way as above. NC. And here we have FC, which is R free R module over the endomorphisms of that object. So how could you define this F bar of C? Well, there is a distinguished element in here, which is the identity of C. This is an element of this R module FC. It's just maybe an abstract way. I mean, the notation makes it complicated maybe, but this is just an element in FC, this R module. The identity is distinguished element. So let's try to map that somewhere. And, well, we can map that element to an element in NC. So this certainly lands somewhere here. Let's call that N0. Or let's call it NC, why not? Okay. This lands somewhere here. This has a preimage because that's an epimorphism. So there certainly exists, not uniquely, but there exists something like that. Okay, so somehow I'm a purist and it bothers me that this is not blue now. Let me make it blue. So a natural choice is to map this element to this MC. So set, that's a definition, F bar of C, that's an R module map, and this R module map should map the identity to MC. Definitely F bar has to satisfy that. And now I'm claiming that out of naturality, out of the fact that all these maps need to be natural transformations, there is only one choice. Everything is done. There is no other choice. We can extend this map now. This determines everything. So for that, we need to say, so let me think. Right. So if you have any map between objects, or any map to an object D, C is our fixed object, so as an element in the morphisms from C to D, and this I view as an element in FD, remember, free abelian group over this set. So now this is an arbitrary basis element of FD as an R module, and I want to define F bar D, and therefore I have to tell you, what does F bar do to such a basis element? Well, it does the following. We define force by naturality F bar D, so that's a map now of R modules, applied to this element So now let me write this element as, in a complicated fashion. Sorry, this should be phi, not D. Okay. Just writing in the complicated fashion. But remember the RC module structure on this, remember the fact that F bar should be a natural transformation. This forces something on us. It forces that this is equal to M of phi applied to F bar C of the identity. And this is in MD. Okay, let's look slowly at this. Whatever we have, it definitely should land in MD. That's good. F bar C applied to the identity lies in MC, and is this element MC that we just have chosen. And the fact that we can somehow pull out this phi, by M phi is just the fact that F bar is a natural transformation from F to M. So it's not clear yet maybe that that definition really does what it should, but as soon as we define what happens to this identity element in FC, we're forced to define F bar like that. Then we have defined it on any basis element on any FD, and therefore it's completely defined. So that's the only chance we have, and it turns out, and that's something that you can now check, and I won't check in more detail, that this really defines a natural transformation. And it's not hard.
But it does, of course, depend on the choice of this pre-image. M's, what
right.
is it called?
That's the only choice, and there are several choices. Again, we've seen in the definition of projectivity, it's not a unique lift, but that's the only choice. And it also solves the lifting problem. That's something that we had a situation where we had a trick like that. And that appeared, I think, in the proof of either the homotopy invariance of singular homology or excision of singular homology, where we wanted to define a chain map and we wanted to define it on every singular simplex, and we started by defining it on the identity simplex, and then by naturality extended that. And that's in a very similar spirit like that.
Yeah, in the excision proof that happened, I think.
Yeah. All right, so let me give you an example of a free module over some category. And the category I want to look at is the category of topological spaces. And the module is the nth singular chain group. That's definitely a functor from top to R modules. And I'm claiming that this is a free RC module with model delta n. Yeah, why is that? Well, that's almost by definition, because how is the singular chain complex defined? Well, it's the free abelian group on the maps from delta n to our space. So I could write this as the free abelian group on the morphisms in our category, which is just topological spaces, but let me write it now with C, from this model delta n to whatever module I plug in. To whatever topological space I plug in. So by definition, this is a free module.
So in some sense, it's a rank 1 free module, yeah, because there's only
it's
one.
It's a rank 1 free module, yeah. Yeah, with that model. So we have the following theorem that's very similar to the fundamental theorem of homological algebra. So let F star be positive free RC chain complex let M be the set of modules for all of the Fn's. So let M be a set containing all models of all Fn, put them all together, and let G star be another chain complex of RC modules. Such that the homology of G star at a model is 0 for C in M and N greater than 0. And then I claim that the natural map from the chain RC chain homotopy classes from F star to G star given by the H0 functor to the following homomorphism is bijective. There is a lot to swallow here, but you see this superficial similarity, at least, to the fundamental theorem of homological algebra. So let's go through. So let's for a moment assume that the second assumption is even stronger, that not only is this chain complex acyclic in positive degrees on the models, but let's assume that it's 0 for any object in our category C. So that's a stronger assumption. Because that stronger assumption would really mean that G star is what we would call acyclic. Okay, so it's acyclic at any object. And then we are in a similar situation as in the situation of the fundamental theorem of homological algebra. What's the situation there? There you start with a projective RC chain complex. Here we assume a bit more free. But let's say we would have a projective here and we would have this acyclic condition in the strongest form for any object. Then this would be exactly the same situation as in the fundamental theorem, and the conclusion would also be the exact analog. So the chain homotopy classes, after we apply H0, can be described by homomorphism of what happens on H0. So now these are not modules in the ordinary sense, these are functors from C to R modules. So H0, if I compose this with F star, meaning that I do this for any object. So this is a functor itself here. An object C is mapped to H0 of F star C. And therefore, I can look at the homomorphisms at RC modules. But it's the exact analog, and the proof is exactly the same. If you remember the proof is just going through diagrams and using the projectivity as we have seen it just a minute ago, always using this lifting problem. So the proof would go through verbatim the same if we had the stronger assumption that this is acyclic for any object, and even the milder assumption that we had a projective chain complex. Now the statement is a little different because that's the more useful statement in praxis, where you have a strong assumption here. This is indeed a free chain complex, so it makes sense to talk about the models. And if you then have a close look at how the proof goes of the fundamental theorem of homological algebra, it turns out that you only need the acyclic condition on the models that appear. But it's still the same proof. It's just having a careful look and you see this is the only thing that you need. You don't need it everywhere.
But you need it for all models in all degrees, right? I mean, it's not enough to check that Hn of G star C is 0 for all C in the models of the module
No,
Fn,
you could
or
make
Fn
an even more general statement.
Probably Fn minus 1, Fn,
right,
and Fn
something
plus
like
1
that.
is probably
Right.
enough. Okay.
Right. The thing is, you always use, you solve these lifting problems. And how do you solve lifting problems? You apply this projectivity. And what we did before in proving that a free module is projective is the main task was to show where does the identity of this model go to. And this you do there in any step. And then you need only the exactness of G star at the model, because this allows you to define where the identity goes to. And then somehow the naturality enables everything.
I'm a little confused why you write H naught composed with F star on the bottom. What?
Right, so I view F star as a functor from C to R chain complexes, and H0 is a functor from R chain complexes to R modules.
Yeah, sure.
And then it gives you, Okay, so I won't prove this theorem, and I'm sure you could do the proof yourself using or looking at the proof of the fundamental theorem plus how we did the proof of the projectivity of a free module. But I want to apply this theorem now to obtain this Eilenberg-Silber chain homotopy equivalence. So let's talk about this. What is the category? That's the first question. We're talking about products here, and it turns out the right product category is not top, but top times top. So the category of pairs of topological spaces. And the morphisms in that category are products of maps. So that's the category we're dealing with. And I consider two RC chain complexes.
Not to be confused with the category top 2, right?
Exactly. Consider two RC chain complexes, namely chain complexes that appear in the Eilenberg-Silber theorem. The first one I call F star. It's the singular chain complex, but now as a functor in two variables. So now it's a functor from C to R modules. And the second one is G star. It's the product, the tensor product. So here is the first, tensor the second. Or maybe I should do a double bar to distinguish the two entries. Never mind. Definitely these are RC chain complexes. And we want to apply this acyclic model theorem. So we need a bit more. We need this acyclic condition. We need to know what the models are and whether these are chain complexes of free RC modules. Let's start with F star. So we have for Fn, let's write down what it is in a. So first of all, it is defined as the following. Okay. But I can rewrite this as R and now morphisms in C because a map to a product is just two maps from delta n to the first space and from delta n to the second space. The morphisms in the category C are products of maps. So this is really the same thing, just written in a different way, and so written that we see immediately that this is a free RC module with model delta n times delta n. So free with model delta n times delta n. What about G? So Gn, what is Gn? Well, this is a direct sum. This was the tensor product. And let's spell it out. All right, so what is that? You have two free R modules and you tensor them over R. That's the same canonically as the free R module over the product of these two sets. So that's, in a natural way, this is the same as this. And now I want to give you an interpretation in terms of the category C. So what is this thing here between the brackets? Well, this is nothing else than more C delta P times delta Q. All right. So you see that also G star consists of free RC modules, but so this is a free RC module, Gn, with models this whole set, delta P times delta Q for all P, Q that add up to N. It's a different model set, but it's also a free module. What about the condition that these chain complexes are acyclic? Well, this is now easy. I need that What are the models? The models in the second case were delta P times delta Q, with varying P and Q, and the model in the first case was delta N times delta N. But models in both cases were of the form singular simplex times singular simplex. And a product of singular simplexes is always contractible. It's always contractible to a point for all P and Q. So these singular chain complexes if you plug in these models now, have vanishing homology in positive degrees. Because there are singular chain complexes of that thing, and here a tensor product of singular chain complexes. And okay, so maybe one step back. So the first one is really the singular homology of that thing. That's definitely has vanishing homology in degree 0. That was a tensor product. But if the homology vanishes except in degree 0, the algebraic kernel theorem immediately gives you that that has vanishing homology. Indeed, you don't have to argue with that. You could also argue that the chain complexes themselves are chain homotopic to the singular chain complex of a point, and can argue with that these chain homotopies give you a chain homotopy of the tensor product. But you could also use the algebraic König theorem. Don't have to use the topological König theorem because that's based on what we're doing right now. But you use the algebraic one because that was the algebraic tensor product. Okay, so all the assumptions we need in the acyclic model theorem are satisfied. So what does it give us? The acyclic model theorem. I claim implies what we want. Implies the Eilenberg-Silber chain homotopy result, and this is because now I have to go back to the statement of the acyclic model theorem. The statement was that the chain homotopy class is determined by whatever is happening on H0. But whatever is happening on H0, this was given in the Eilenberg-Silber statement because we said what is happening on zero simplices. And the statement is that that determines a natural chain homotopy equivalence. The nature is built in because we are talking about RC modules, so these are functors from C to R modules. So the naturality is built in that statement. And it's a direct consequence. And that proves the Eilenberg-Silber statement with a lot of machinery, but with almost no computation.